Let's start on the script 7a. So far, we have created a composite image for a particular admin2 region. Now we come to the core of remote sensing analysis. Our goal today is to detect water from satellite image. One way to do this is to use a spectral index. I want to just give a brief recap on spectral indices. If you had watched the introduction to remote sensing video that was recommended for this class, each material on the Earth's surface has a unique reflectance in different wavelengths. And this is what we can use in remote sensing to identify the material. If you look at the reflectance of water, it looks something like this in different bands. So on the x-axis, we have the blue, green, red, NIR, SWIR 1 and SWIR 2 bands. And on the y-axis, we have the reflectance. This shows how much of the light is absorbed and reflected. So you can see water typically has a higher reflectance in the green band and low reflectance in infrared bands. Vegetation, on the other hand, has a very high reflectance in infrared, near infrared bands, and it absorbs most of the red light. Built-up regions have a high reflectance in the shortwave infrared band. Soil has a very high reflectance in SWIR band, along with high reflectance in NIR band. So you can see each material has this unique spectral signature, and we can use this to say if the material looks like this in the spectral regions in different bands, we can extract that. The one way to do this is to use something called index. If you have an image like this, we can take and we want to extract, say, identify vegetation. We can say vegetation has a unique property where the near infrared band has very high reflectance, red band has very low reflectance. No other material has a similar property. So we can leverage that and say, I will take the ratio of the near infrared band and divide it by red band. And that value, NIR divided by red, will be high wherever there's vegetation. It'll be low in other materials. And if you just divide two numbers, like NIR reflectance versus red reflectance, you will get arbitrary values. You will get values that may not have a specific range. So in remote sensing, we typically do a normalized difference. So instead of dividing two bands by each other, we can just say, do NIR minus red divided by NIR plus red. And this always ensures that your values are between -1 to +1. And you can also interpret that the values have a meaning where you can say values like 0.5 is high, which will be higher healthy vegetation and so on. Similarly, water, there's an index called NDWI, where if you take the ratio of the green and NIR band, only water will be high in this particular ratio. And you can use this to detect water. Built up, you can take the ratio of the SWIR and NIR band. Right? So there are a lot of the indices in remote sensing which can be used to detect different materials. So let's see how to compute those indices. And we'll focus on water. We'll learn about some indices around water, and we can see how to use that to extract water. On the script 7a, let's first learn the basics of doing the index calculation. We'll first create a band of NDVI. So NDVI is one of the most popular indices where you take the ratio of the near infrared and red band. We are working with Sentinel-2 data, and in Sentinel-2, we look at the documentation. We want the ratio of the NIR and the red band. We come here and we say NIR band is band number 8, red band is band number 4. So we can use those bands to compute NDVI. We have the image, which is a composite image, and the function to compute index is this function called normalized difference. Because you have to do this very often, so Earth Engineering gives you a helper function where you can run this function normalized difference, give it a list of two bands whose normalized ratio you want, and you'll get the result. So we can give the ratio of the band 8 and band 4. So we have our index. Let's visualize this. You want to add it to the map. Again, we want to clip it to the geometry. We need some visualization parameters. So I'll define some parameters here. What would be the min and max that is appropriate for NDVI? -1 and 1, this is a theoretical min and max of NDVI. So NDVI should be between those. That's a good starting point. Though NDVI could be as low as -1, and as high as +1, you will see that in most of the urban regions, NDVI is typically between 0 and 0.7. Again, you can start with that and you'll realize that my image is very low contrast. And then you can do your 98th percentile stretch and figure out what's the right value. So let's do a 0 to 0.7, which is the more common range of NDVI that is observed in an urban region like this. Let's do our NDVI viz and name the layer as NDVI. You can see a new image being loaded. It's a grayscale image. The low values are darker, the high values are brighter. Let's zoom into some region. So you can see this. I like to show this example because you'll see that the water appears kind of green here, right? This water is also green, the vegetation also green. But if you compute NDVI, you'll see that the water has a very low NDVI and the vegetation, healthy vegetation, has very high NDVI. So again, what human eyes cannot see, the satellites can also see that, right? So you can see very clearly which is water and which is vegetation. Let's use the inspector to inspect some values. I can inspect here. And you can see the NDVI value is 0.68 here. If I inspect somewhere in water, you will see that NDVI will be very low, negative NDVI. Right? So this shows you that you can kind of use this index to differentiate different materials. When you have a one band image like this, so you just have one band of data, right? You have NDVI low to high. You can visualize this in any color that you want. You can give a different palette. So I can give one more parameter called palette, and I can say visualize this between white and green. That means zero values, 0 and lower will be white, 0.7 and higher will be green, and all the intermediate values will be a shade of that green. Okay? So let's run this and see how the new NDVI layer looks. So now you can see this layer in green. And this shows the regions of low and high NDVI. One thing you'll notice is when I inspect this, when you run this function normalized difference, the output image has one band. The band is always called ND. ND stands for normalized difference. So if you have an image, you can see my band name is ND. If you have an image containing multiple indices, they'll be all named ND1, ND2, ND3 like that. And that's not very useful or informative. So what I like to do is whenever I run this function normalized difference, I can run one more function called rename, which will allow to rename the default band name that comes out. And we'll just rename it to be NDVI. This helps when you are computing multiple indices, you can identify those much easier. Now, when I inspect this, you'll see that my band will be named NDVI. Yes, instead of ND, it became NDVI. Okay, let's continue and let's compute the next index called MNDWI. We saw that there is this index called NDWI. This was developed, one of the first water indices to be developed. This was developed in the era of Landsat 5, I guess. The Landsat earlier satellites didn't have a shortwave infrared band. So the best you could do was to use the NIR band, and you can compute this ratio. All the modern satellites also have the SWIR bands, and you can see the water reflectance is even lower in the shortwave infrared band. So a better index for water detection is something called MNDWI. This is the same kind of form as NDWI, but it's a modified NDWI that uses the SWIR band instead of the NIR band. So let's compute the MNDWI value. Same thing, we'll use image, normalize difference, control space to autocomplete. And now we'll give it the band 3 green. And instead of band 8, we'll give band 11. That's for MNDWI. And we can just copy paste some code and modify it. So I'm going to take this and use a similar same thing with NDWI. NDWI also has the range, anything greater than 0 is usually water. So we can probably go like negative 0.5 to plus 0.5 just to kind of see the difference. And we can visualize this in a blue color. If you're doing water detection with Sentinel-2 or even Landsat 8, MNDWI performs much better than the default NDWI. So I recommend you use that. And as the layer is being processed, you can see this progress bar. It's being computed in real time, and you can see that being loaded. So you'll see that the water body in our region has a very high NDWI value. I can use inspector and check you'll see the water bodies typically have greater than 0 NDWI, and other non-water bodies will have 0 or negative values of NDWI here. Many of the indices will take form of this band ratios, and you can use the normalized difference to compute that. One of the problems that people working with water faced is NDWI is great. It is very reliable to detect water, but you can see there's no fixed threshold for detecting water. So in this image, I can say I'll inspect around here and say, okay, let me see what is the NDWI here. It is 0.27 and negative 0.27. And here it's negative 0.5. So here in this case, anything greater than negative 0.2 is water. And so the threshold really varies between place to place, depending on and even time to time. So if you want to do a time series of water detection, for every time step, you have to go manually and figure out the threshold. So to have a more reliable threshold, another index was developed called AV. So AV, Automated Water Extraction Index, aims to create an image which has got a stable threshold of 0. So regardless of your image composition, anything above 0 is water, anything below 0 is not water. And it uses the combination of different bands to arrive at that particular threshold. And the formula for AB is this. It's 4 times green minus SWR2 minus 0.25 times NIR and plus 2.75 and SWR1. In our course material, we've linked to the paper, AV paper. You can read it and kind of see the rationale, how it was developed. But for now, let's learn how to implement this index and see the results on our map. So how do we implement this very complex formula? We can't use normalized ratio because it just, there's no ratio here. It's just some multiplication. So Earth Engine also gives you one more function called expression. Let's look at the documentation. We will use the expression image.expression. This function takes 2 parameters. An expression, so you can write an expression in a natural language, and then you can give the second argument is a dictionary of all the parameters that you used in your formula. Let's see how we can implement this using this. So the first one is the expression. So what's our expression? We can just substitute this as our expression. So we can just use directly this as our expression. Right? So this is the expression. That's what we want to compute from our image. Now this expression, the green SWR1, doesn't really have any meaning. We have to tell Earth Engine, what do we mean by green? So that's where the second parameter comes in handy. We can say, have a dictionary. So the second parameter is a dictionary of the different parameters. So we can say green. Here, what we mean by green is actually the image.select the green band. And the green band is band 3 here. So wherever in the formula you see green, you replace it with the value from the band 3. Secondly, we have the SWR1. Wherever you see SWR1, replace it with the value from the band number 11. And then we have NIR band. We substitute that with band 8. And then finally, we have SWR2, which is the band 12. And now what we get is an image which will be computed using this formula, and we can rename it to be automated water detection index. So this is a very flexible way to do any formula. This formula supports all kind of common mathematical operations. If you have exponent, logarithms, all of this can be defined here. All you need to do is replace all the variable names with whatever bands are there in your image. And again, you can just do a formula like x minus y. Doesn't matter. You just have to say x is this and y is this. Right? It doesn't matter what variable you use. Whatever you use, you have to say here, wherever there's x, replace it with this. It's good to use the more descriptive names here so you can kind of debug it. But again, it doesn't matter what names you use. So this is how to compute more complex indices. But here there's one more problem. If you look at inspect any pixel values, you'll see that the pixel values that we have look like this. So here, if we use this formula, formula says take the green reflectance, subtract the swirl reflectance. So if for this pixel, if we want to compute this, it'll take the band 3, 556 minus 1685, right? And this is not what the formula expects. Formula says whatever values you put here has to be reflectance. These are not reflectances. As we saw earlier, the Sentinel-2 image comes with a scale factor. That means the pixel values are 10,000 times what the reflectance is. So to get to the reflectance of that particular pixel, you have to multiply each band value by the scale factor. So what is the reflectance of this band 3? Well, you multiply it by 0.0001, that'll be 0.05. That's a reflectance. What's the reflectance of band 8? 0.3176. So if you're using this formula, you have to actually substitute those values of the reflectance, not the pixel values. Even the other formula, NDWI, NDVI, they also are based on reflectances, but we need have to do this because when you take the ratio of two bands, they'll cancel out, right? So, or they have the denominator and numerator have the same scale factor, they'll cancel out. So we didn't have to do it. It's a good practice to do it, but again, it doesn't matter because they'll cancel out. When you have a formula like this, you have to make sure that you are keeping the actual reflectance values and not the multiplied values. Can anybody tell me why don't we have the reflectance values directly in the image? Why we have to multiply it with the scale factor? Exactly. So the reason for the providers not giving you the reflectance values is because if you want to store reflectance values, you have to store them as floating point numbers. Typically a 64, it'll take 64 bits to store one number. If instead you store them as integers, you'll take only 16 bits. And that means you save 4 times the storage space per image to store this. And Sentinel-2 itself is producing 5 terabytes of data every month. So you definitely want to save on that disk space. And let's say users who are using this data can convert on their end. So that's why we have to do this little bit extra work to convert this data to reflectance values. So let's just do it ourselves. We'll just say, I will multiply it with the scale factor. And we'll do it for all the bands. And then finally, we will have our result. Let's add it to the map. We'll use the same which parameters as NDWI, so we can compare and contrast how the AB versus NDWI look here. You see the difference now? MNWI has more variation in the range. AB is 0 and 1, right? Like anything greater than 0 is all blue and it's much more cleaner. So AB is kind of, if you want to do automated water detection, you can say, I'll compute AB greater than 0 is water, and that usually gives you much cleaner results than using NDWI. NDWI is actually more reliable and more robust, but you need to compute the threshold manually. We'll see some of the techniques, but again, this is kind of an index that a lot of people like to use for doing more automated water detection. There's a question on which one will be more reliable, an example use case. Well, in my experience, MNDWI is much more accurate on a global scale. So if you are willing to put in the extra work to compute the threshold, either manually or by other automated means, then MNDWI is generally is more accurate. If you just want a simple index that you say, I don't care, I'll just do a simple threshold and get to my image, AB is better. So again, as with everything in remote sensing, it really depends. And that's why there's no fixed answer. But if I was working on a project, my first choice today will be MNDWI with Sentinel-2. There are techniques which you can use multiple indices. When we cover unsupervised clustering in this course, we'll take 3 different indices and we'll say, give me the best of all 3 and detect water using that. So again, you can do an ensemble of different indices to do a much more robust detection. There are 2 equations for AB. We're going to cover those two equations in the exercise. So there are two versions of AV, where if you read the original AV paper, they figured out that a lot of the building shadows or dark regions of your image, they're very similar to water. And AV generally gets confused between shadows. So they developed an alternate version of AV that is more robust for building shadows. We're going to see that in the exercise. So again, a lot of times when you're doing the research, you figure out, oh, this works really well for my region. And then you try it in a different region. The reflectances are so different that it doesn't work well. So again, all of this will really depend on the region. You can experiment and see what works best for the region and time period that you are trying to work with. Good question. Can we multiply all the image bands with the scale factor automatically? Yes, you can. And that's the recommended practice. We'll do this. But to do this, you'll need to learn about MapReduce. That's coming up in module 2. Once we learn about MapReduce, you'll see that in the code, we'll start by filtering our collection. So we'll filter our collection and immediately map a function that will scale all the bands. For all images, all bands, right? And that's the one step, but we'll have to wait to learn about MapReduce before we can do that. All right, let's do the exercise.